Okay, so now I want to look at assignment 11 right here. And assignment 11 should be our easiest question. It's our easiest assignment. It's on equilibrium right here. Remember, the definition of equilibrium is the sum of the forces equals 0 and the sum of the torques equals 0. And this is going to be true about any point because no point is accelerating when you're in equilibrium right here. So we have, you could take this about any point you wanted. And since this, remember our last chapters, this was equal to MA and that was equal to I alpha, well, 0 is definitely a lot easier right here. So this chapter should be the easiest. Now this chapter also goes through something called stress and strain. And in this class, there's really no stress right here. We're not going to have any stress in this class, so you can skip that part. This is the only part we're doing for chapter 11 right here. And remember, the definition of torque is R cross F right here. But if you don't like to use the magnitude of the first, magnitude of the second times the sine of the angle between them, it's a lot easier, especially in this chapter. Instead of saying R cross F, just say it's the force times the shortest distance from the point you're taking torques around to the line of force. You'll see what we mean. And this would make it a lot easier to do some of the torque equations. So here, what I have is I just have, like, say it's a ladder leaning against a wall right here. And I'm even going to make this a smooth wall just to make it a little simpler right here. So there's no friction on this one right here. There is friction on this one right here. And this is in equilibrium. It's not moving. It's just leaning against this right here. Now, if we just draw the forces, again, it's important to draw the mg from the middle. It's the center of mass right here. We also have two normals because we got a surface there and a surface there. So we got an N1 and an N2. We have a friction. Remember, this thing wants to slide that way. So the friction is in that direction right here. So we can first write out the force equations right here. I'll call everything to the right and up positive. It doesn't matter because there's no MA here. So if we look at the sum of the forces in the X, what do we got? We got just the friction minus N2 equals 0. There's the force equation. For the forces in the Y direction, we just have N1 minus mg equals 0. That's it right here. Now, for the torque equations right here, we can call going around this way positive or going around the other way positive. It doesn't matter because when you sum up the torques, it's equal to 0. The only reason why we'd all want to do it the same way is so when I grade it, it makes it easier for me. So what we'll do is, for any of these equilibrium problems, we'll put all the torque equations, we'll make clockwise the positive direction, which really means inward is positive, but we'll go around this way as positive right there. And we can take torques about any point we want. We can take it about A, we can take it about B, we can take it about C, D, E, F. You can take it about this point over here. So you got an infinite number of equations. They're just not independent of each other, right? You can't find an infinite number of things, but you can take it about any spot you want right here. So right here, I said, let's take it about different spots. And I said, let's take it about this point, A. It's always good to take it where there's a lot of vectors, forces, because then I can ignore these, right? Because any force that goes through these points, remember, the shortest distance from this line to that point is 0 right here. So it's good to take it about where, matter of fact, but if you wanted to solve for these guys, you probably wouldn't want to take it here because it wouldn't be in your equation. Okay, but let's take the torques about this point right here. Now, the torques about this point, we can forget about these two because they both go through that point. We only have to worry about these two. You notice this one is trying to drive me clockwise around that point. This one is trying to drive me counterclockwise. If you can't remember which one it's doing, just put your pencil there, pivot it right there, and push with mg. You notice it's going clockwise. If I push with N2, it's going counterclockwise. And we said we'll do the clockwise as the positive. So what do we got? We got mg times the shortest distance. The shortest distance between this line and that point? Well, just to give you some distances, since this is L and that's theta, this is L cosine theta, and that is L sine theta right here. So when we do the torques this way, we have mg times that distance. Well, that's right in the middle, so it's half of an L cosine theta. Minus, since this is going in the counterclockwise direction, it's n2 times the shortest distance between this line and that point, which is this distance right here, which is just L sine theta, and that equals 0. So this would be a good spot to take torques since usually you know mg and theta. If I wanted to solve for n2, this would be a good spot to take torques on. If we were to take the torques about that point, say B right here, and then I don't have to worry about n2 because it's going right through that spot. All I have are these three. You notice n2, n1 right here, if I push with n1, it's going around this way. Friction is going around this way, and mg is going around this way, right here. We said we were going to do the clockwise, the positive, which is n1. So we have n1 times the shortest distance between that line and that point, which is what? That distance, which is L cosine theta, n1 L cos theta, minus mg, which is this right here, it's going around this way, times the shortest distance between this line and that point, which is that distance, which is half an L cosine theta, minus the friction, which is going around this way, times the shortest distance between this line and that point, which is this distance, which is L sine theta, equals 0. And then I said, let's pick the middle right here, the C right here. Now, at that point right there, I don't have to worry about mg, but I have these three I have to worry about right here. The clockwise one would be n1, that's going around this way, and the other two, friction and n2, would be the negative ones. So we've got n1, shortest distance, which is that distance, which is half an L cos theta, minus n2 times that distance, which is a half an L sine theta, minus the friction times that distance, which is a half an L sine theta. Now we can take it about other points. It didn't even have to be on the object. I picked D right there. D is right where these two forces intersect, and so I can ignore these two vectors right here. The only ones I have is friction and mg. We can see mg is going around this way around that point D. Friction is going this way. So we have mg times that distance, which is L over 2 cos, minus the friction going this way times that distance, which is L sine theta equals 0. So it might be good to write these lengths out if you had a problem like this. If I asked you to write torques about different spots, just so, because you're using these distances so much right there. Okay, make sure you can write these torques about different points right there. Now the only new force that we'll have is a hinge. Our hinge will look something like that right there. It's just a little pin stuck in there. So this thing could go like this right here, but I'll hold it up here with a rope or something. But now the normal force on a round peg could be in any directions. But what we'll always do is we'll just say for all of our hinges, we'll just break it into its components of normal. So it has some X component and Y component. That's the only new force we'll have. It's still normal, but we're just going to, so all of our hinges will have an X and a Y, and there won't be any friction on our hinges right there. Okay, so let's just say we have here, and we'll just put a couple of hinges right there. Here I have a hinge and another hinge, and I have a stick coming up like this and another stick coming over like this, and I'll drill a hole through the two and put a pin in there. So I actually have 3 hinges right there. And I'm going to make these the same mass, but this one must be a little skinnier because he's longer right here. And the length from here to here is L right here, and this angle is theta right here. So now, remember when we looked at forces, we looked at each object individually right here. So I'm going to look at the forces on, say, I'm going to put all the forces on this top stick, we'll make it in green, and everyone on the red stick, I'll make it, sorry, on the diagonal stick, I'll make it red. So over here, I have two normals right here. I just have to figure out what the vertical and the horizontal one is. Well, you notice if I were to pull this pin out, this thing would drop right here. So this normal must be holding it up. So I'll call that NY3 right here. Also, this thing wants to come out, you know, this thing, if I were to pull this pin out, not only would it fall, but it would come out of the wall because this one's going to fall down like this. So this must be holding it to the wall right here. So the NX3 is this way. This one better be opposite because we know the sum of the forces is 0. So if this one's pointing that way, that one better be pointing this way. And then also, if we look at the torques about this point, this mg is trying to bring me down. This one must be opposite, so it must be up right here. So now we've got all the green ones right there. Now the red ones, first of all, this red should be opposite because these are equal and opposite forces right here. So these two red should be the same as these two green right here. We have this one. We know the total force on the x should be 0. So if this force is this way, this one better be in that direction. So NX1 is this way. And I can see that if I take torques about that point, mg is trying to bring me this way. NX1 is trying to bring me this way. NY1 better be fighting it. So I have to have it going this way right there. Okay, so now I have all of the forces. Now I can write out the sum of the force equations on each object. So the sum of the forces in the green, we got NX2 right there minus NX3 equals 0, which means NX2 and NX3 are the same. And then the forces in the y, we got NY3 and NY2 minus mg equals 0. And then we'll take torques, say about that point right there. We've got mg times the shortest distance, which is L over 2, minus, we don't have to worry about these, any of these three, because they all go through that point. We only have to worry about mg and ny2. So you got minus ny2 times the shortest distance between this line and that point, which is L, and that equals 0. So I could get ny2 from that right there. Okay, now let's look at the forces in the x direction on the red right here. NX1 minus NX2 equals 0. And if we look at the forces in the y, we got NY1 minus NY2 minus mg equals 0. And then if we look at the sum of the torques, I picked this point down here. We don't have to worry about these two. We got mg times that length, which we called L over 2. It's the same as that. Plus ny2, which is this force, times that length, which is L, minus nx2 times this length right here. Well, since I know that length is L, I know the opposite, and I want to get the adjacent, it looks like I have to use the tangent. The tangent of theta is L over this distance, or this distance is L tan theta right here. Okay, so there's all my equations right there. So it looks like we can solve for ny2. Well, we can get from, which one? Actually, from this, we can see nx2 equals nx3 and nx1 equals nx2. All the nx's are the same right here, okay? ny2 I can get from right here, which is mg over 2. Cancel the l's. And if this is half the weight, and this must be the other half of the weight, because it equals mg. So these two were just equal to half the weight right there. Now if I wanted to get ny1 right here, I could come over to here. ny1 is mg plus ny2. So it's this plus mg, so it's 3 halves mg. So it looks like NY1, this one right here is holding up most of the weight right here. Because this is 3 mg, the other two are only holding up half the weight right there. Okay, and then if I wanted to solve for NX right here, I could get NX2 from right here. Since we know NY2 was half the weight, and this is the other half of the weight, so that just gives you MGL. The L's drop out, and you get this, NX2 right here. You'll notice, if this angle, if this thing were pivoted way up here instead of way down there, this theta would be a lot bigger. When theta gets close to 90 degrees, the tangent of 90 degrees is, when this thing gets really huge right here, this thing right here becomes close to 90 degrees right there, and so this thing is, if you're going to put a lot of weight on here, you don't want this thing way up here. You want this thing, you don't want this thing big. You don't want this length small. You want this length big right here. So if you're ever building a ledge and you want to put a lot of weight on here, don't put these two hinges right next to each other. You'll rip this thing right off the wall right here. You want to get this distance kind of large right here. Okay. Over here I don't have any hinges. It's just a stick being held to the wall by friction, and then I have a rope coming up like that, and just friction's keeping it from falling down right here. So we have the normal, we have the friction right here, we have the tension, and there's a weight hanging on this stick, and you have another mg right there. They're equal weights. Now I could call that another tension because it is a rope tied to a mass, but whether I just clip the mass right on that point or put a rope to it, it doesn't matter right here. So I'm just going to say there's another mg coming down right here, and it's 3/4 of the way out right here. And what I want to do is I want to say what's the maximum theta can be right here, because if this angle is too big right here, if you tied it way up here, this thing would just slip down right here. So let's look at the forces. What do we got? We got N minus T cos theta equals 0. This is an equilibrium. The Y forces, you got friction plus the T sine minus 2 mg's equals 0. And then if we look at the torques, I said about that point, so I don't have to worry about these two forces. All I have is an mg going down around this way times L over 2. And we have another mg times 3/4 L. So you got mg L over 2 plus another mg times 3/4 L. And then you say, what is the torque this way? Well, you could do it two ways. You could say it's the force times the shortest distance. There's the shortest distance right there, and that would be 90 degrees. So this is a right triangle. And if that's L, that length would just be L sine theta. So you could do it that way. Or if you want, you could break your T into its components. You could call that T sine theta and that T cos theta, and you could ignore the T cos theta because it goes right through here. The T sine theta, the shortest distance is L, so it'd be T sine theta times L. So it's the same way right here. And if we're on the verge of slipping, we can say the friction equals mu Sn right here. Okay, and so now we can just come back up to here, plug in our friction. Remember, our N is T cos theta, so this is T cos theta. And I can plug that right up into here. So you got mu S T cos theta plus T sine theta equals 2 mg. We could solve for T right there. We can get T from this equation right here. From this equation, we can solve for T. Combine these two together right there. And then take that T and plug it up into these two spots. And that's what I did. And we can solve for mu S right there. And so this thing I can combine, put that term together right there. And so we end up with the cotan of this angle has got to be equal to 3 over 5 mu s. That's the biggest this angle could be. It could be smaller, but it can't be bigger than that right here. Otherwise, this thing would just slip down right here. This last one here, I just have a block pushing it on a smooth surface. Since this is smooth, it's not in equilibrium. This thing is accelerating. But I'm going to assume it's not, I don't want to, it's at least in rotational equilibrium. I don't want to knock this over right here. Well, if we look at the sum of the forces in the x, you just got F, that's it. There's no friction, that equals ma. And then you have n minus mg equals 0 for the up and down right here. But if I tried to put friction, remember we have to find torques about that point because that's the point. Remember, if you're accelerating, you have to pick the center of mass right there. Well, if we put the normal here, right there, and then we don't have to worry about the torque due to the normal or the weight, and you just have one torque. Well, if you only have one torque, you're not in equilibrium. This is just going to tip over. So what happens here is when you try to push this, this normal force starts to shift. It starts to shift way over there. It can't go any further than that. Matter of fact, pretty soon the block will actually get up on that corner right there. So this friction moves all the way over to here. Once it gets to there, you push any harder and it's probably going to tip over right there. So let's look at when you're right there, what do you have? When you look at the torques about that spot, you got F times this distance. Well, if that distance is h and that distance is L over 2, then that little distance here between them is h minus L over 2 minus the torque the other way, which is N times, that was W is the width, times half of the width equals 0. And so solving for F right here, just throw that down below, there's what the maximum you can push right there. And you notice if W is bigger, if this is wider, you can push a lot harder right here. If W, if you're trying to push a real skinny object, it's going to tip over right away, right there. And then there is the maximum acceleration, because if you know the maximum force, you know the maximum acceleration right there. So we can get, all I did was just take this and divide out the m right there. So there's the maximum acceleration. Okay, so this is all I'm going to talk about with equilibrium. You just write out the sum of the force equations and the sum of the torques, and you can pick any point you want, but if you're trying to solve for t, that would be a good spot because usually you're not given the normal and the friction right here. You probably don't want to put it where you know things because you don't want to get rid of the stuff that you do know. You want to get rid of the stuff that you don't know. Okay, so hopefully this will help. Okay, there's one little thing I wanted to correct on this. There was a little mistake here. When I said the tangent of theta is L over y, let's just call this distance y right here. So that means that the tangent of theta is equal to L over y, or y is equal to L over tan theta. So this should have been L divided by tangent theta and not L times tangent theta. So this should have just been a divide by the tangent of theta, which means that this should have been in the numerator. This is the tangent of theta right here. That makes a little more sense to me because when these 2 points get close together, this angle goes to 90 degrees when the tangent of 90 degrees is infinite. So that's why I said this nx2 will go off to infinity when you bring these close together. If this was a long ways down here, this angle is small. When theta is small, tangent theta is small, and this becomes 0. So you don't want to put, if you're going to hold up a heavy ledge right here, you don't want to put these 2 points close to each other, right? If there's a bookshelf or something like that, you want these two to have some spacing. Okay, so that should have just been, instead of L tan theta, it should have just been L divided by the tangent of theta.